So maybe we can get started back. So a quick notice is, so the lab are going to start at 2:30. So they're going to be the building next one over. 2 is a classical. It's 2. Last. So they're going to be in the next building over. So similar to this one. Alessandro Raffaello literally put pieces of paper with regML everywhere. So it should be pretty hard to get lost, but you have our phone numbers, or drop an email if you find yourself in a scary corner of the building. Okay, so as I said, we're going to go pretty fast, okay? So the first part was not that fast. It was basically recovering the main concepts of statistical learning theory, the data, distributions, loss function, expected risk, and lastly introduce the notion of hypothesis space, okay? What I'm going to do now is I'm going to introduce algorithms, and the way we're going to do it is by sticking to linear models, okay? Just linear functions for quite a while, and then make the jump towards first nonlinear features, okay? That's going to be more or less for free, and then with a little more effort in terms of abstraction to kernel methods, okay? So the protagonists of today's class are going to be the so-called Tikhonov regularization, arguably the most classical kind of regularization, and eventually we're going to introduce the notion of kernels. So, I'm get distracted. Me la chiudi? So again, make a distinction between what you would like to do and what you can do. Okay? What you like to do is the definition of the problem. What you can do is the algorithm to solve that problem. Okay? So what we would like to do is to minimize the expected risk, which is the average loss function with respect to the true distribution. This we cannot do because the distribution is assumed to be fixed once and for all, but it's unknown to us. And it's known only through a set of pairs, xi, yi, that we're going to assume to be always independently and identically distributed with respect to rho. Okay? Just as a side remark, many of the algorithms that we introduced works also for other settings. The independence assumption can be tackled pretty easily. The identical distributed assumption, as you can convince yourself thinking about it for 20 seconds, is crucial. Because here we're basically assuming that the more data we get, the more evidence we accumulate with respect to something that is fixed once and for all. If that something changes, it's a whole different game, okay? So we do make this assumption. So we would like to solve this. All we know is this. What do we do? What is the first idea possible? Well, you cannot compute this data. We cannot compute this with data exactly, but you can, you can compute it in an approximate way. So what you can do is that you can replace the expected risk with the empirical risk. If you look carefully, you see that there is a hat in one of these two equations. And that hat actually does matter. I usually try to use hat for empirical quantity, and this is indeed an empirical quantity, which is just the sum of the errors over the training set. Okay? So think of this as an empirical mean with respect to the true expectation. So the idea is that we could do something like this, and this is indeed computable. Okay? Because this is now on data. We still have to specify the space of functions, but we might be good enough. Is it? Well, the idea here is that, in fact, in general, these two quantities might not be that close, okay? It will depend on what? So you think these two problems are going to be close or not? And what do you think it might depend on? So for sure it will depend on the size of the samples, okay? If you have tons of examples, then likely these two are going to be close, okay? But these tons of examples, what does it mean a lot? How can we measure a lot? There is another quantity here, which is age, okay? Suppose that age is very small, one function, okay? Or two. And then again, these two problems are likely to be close. But suppose that age is huge, okay? Then these two problems are likely to be far apart. Make sense? So it turns out that in general, given the fact that you cannot control how many points you have, you might want to slightly change this in order to account potentially on the fact that the space H can be so big that these two problems fall far away from each other. And this is the basic idea of so-called regularization. The idea is basically that instead of this problem, we're now going to replace it with a new problem, okay, which is somewhat a perturbed version of this problem. The first part is just the same as before, is the empirical error on the data. The second part here is essentially there is what you call the functional. So what is this? This is something that if you give me a function, it's going to return a number. The intuition is that if the function is complicated, that number is going to be big. If the function is simple, that number is going to be small. Okay? I'm going to make an example in a second. But what you see is that the moment you introduce this, you're basically saying, yeah, I want to make the error small, but with a simple function. And now you have a trade-off between how small is the error and how simple is the function. The typical situation here is if you allow yourself a very complicated function that allows small error, potentially getting too complicated to be good for future data, you did what is called overfitting. On the other hand, if you actually take a function which is super simple, you make these very nice, but then these are essentially ignoring the data. This is what you might call over-smoothing, okay? And the whole game is going to be on how we encode the notion of smoothness or simplicity of the function space and how we trade off these two terms, okay? Most of our discussion is going to be about on way to basically example of how to choose this regularization and how to compute this corresponding solution. This is what we're going to mostly do. Okay? Notice that this is so popular as a way to try to regularize that is sometimes called regularization. Okay? This is in fact, is one instance of regularization, what is called regularization by penalization, or Tikhonov regularization. Tomorrow we'll see that there are other ways to regularize, that is to control the complexity of the solution, which has nothing to do with this idea of adding a penalty term. Here are a few examples of regularizers. Something that we're not going to do is try to derive what is the meaning, the deep meaning of each of these regularizers. Okay? Let's begin with the case of linear models over some dictionary, and truly think of linear models, okay? It doesn't really matter. What you have is that the first example of regularize is the so-called L2 norm, okay? There are many ways to think of this, but the simplest way is think of this as a budget on each coordinate or on each feature, okay? The idea is essentially, if this P is very large, given a certain amount of data, then I can do a lot of crazy things. But if I make P small, then in some sense I'm constraining the complexity of the model. Okay? Now here, the way you constrain P is not quite choosing the P, but rather constraining the budget of weights. Okay? If you allow this quantity to be very large, you can put a lot of weight, a big coefficient on each individual feature. Whereas if you allow yourself a very small budget, then you basically are throwing away, you're shrinking the importance, the relative importance of the features. Does it make sense? So if you view this as a budget on the importance of each dimension over each features, basically this one is just another way of doing the same thing. We will see that while they look almost the same, so this is the square of the Euclidean, or if you want the L2 norm, this is the L1 norm. Here, this is the sum of the square of the coefficient, here the sum of the absolute value, so they almost look the same. You will see that, in fact, they behave quite differently. So basically, today and tomorrow is going to be about studying guys like this, whereas the whole day on Thursday will be on things like this and its generalization. The big difference is that the solution of problem using this will have all the coefficients, potentially small, but different from zeros, whereas if you use something like this, you will set coefficients equal to 0. You will really discard and select, and you will see that this has some advantage in terms, for example, interpretability of your model, because you can go in and say, you don't have to decide what's small. You just say that something is important and something is not. Okay? But this is going to be a whole class on Thursday. And you can keep on going, and for example, you can say, well, you know, if I have a function that oscillates a lot, it should be complicated. So one way to do this is to say, oh, take this function and compute the derivative at each point, and then sum up all the derivatives. If the derivatives are very big, this number is going to be big. If the derivative is small, then this number is going to be small, and it means that my function is flat. Okay? So intuitively, this is a way, this is exactly doing this. It integrates, it sums up the values of the derivative at all the different points. And again, we can keep on going, okay? The list is long. The whole game here is, this is where you put your prior information about the problem, okay? And there are some very general way of doing it and very specific way of doing it. And through the course of the week, hopefully you will see both. So the majority of our discussion today will be devoted to try to understand how to solve a problem like this. Okay? We'll not worry that much about proving that looking at something like this is a good idea. We'll try to just see, once you choose to penalize with the squared norm, how do you actually compute things? Okay? Now, as it is clear from this equation, everything is going to depend on the loss function. It's really simple to see. Notice that, importantly, as I promised you, from now on and for a little while, we're just going to restrict ourselves to the linear case, to the case of linear functions, okay? Of course, at this point, some of you could say, well, do I really need to regularize if I'm just considering a linear function? They look kind of simple, okay? True, but imagine the case where you have 5 points and the dimension of your space is 10,000. You can do a lot of stuff, probably more than what you actually want to do. And still, even in this case, when the case where the number of points is much smaller than the number of dimension, which is kind of our starting point, you still want to regularize. You will see later on that we generalize this to non-linear features, and it's even more obvious. The reason why we stick to this is because computationally, which is our main concern here, everything is in there, more or less. And then you just need to do something complicated on the side. So, again, we're thinking about computations, and we have a functional, we need to minimize it, and the first thing we have to ask is how nice is this functional? And this functional can be pretty nice. All the loss functions we consider are convex, and this term here is how? It's essentially a parabola, so it's not only convex, but it's sharply convex. It doesn't have flat regions. So now you have something that could be flat and goes up, something that goes up, you sum them up, and you destroy the flat regions, okay? So this becomes strongly convex. It's a smile, it's a peaky smile, okay? It's a pointy smile. Now, this we can say to begin with. We can also say that this is continuous. And we are already in a good shape. When you have something which is convex, you're already happy, okay? Notice that here convexity comes from the fact that this depends, the function depends linearly on W, and L, all of them are convex. Now, if we want to take a step further, we have to say something more about the loss function, okay? For example, I told you before that we have the logistic and the hinge. One is smooth, the other one is not. So there cannot be a unified way to solve the problem for all loss function. It will depend on the loss. So the idea is that today we're going to look at logistic loss function and SVM. And tomorrow I'm going to discuss a bit more the case of least squares, okay? The truth is that, the truth is that, up to, if you have to code up the solver of this problem, it is important. To some extent, if you have to use this, and you just choose the loss function you want to use, then the way you solve it is not important for you. So in the lab today, you're going to look at least squares and just to try to understand how to use this, okay? Not how to optimize them. So today in class is going to be just about how it works and how you optimize it. Today in lab is just going to be about turning the crank and see how to use it. And we're going to use least squares just because it's even simpler than this. But today, we're going to discuss logistic and SVM. So logistic regression is kind of nice. Here, remind you the shape of the loss function. Okay? If you remember, this was the one that was a convex relaxation of the step that was smooth and never went to 0, but approached it. Okay? Now, this term is not only convex, but is also smooth in the sense that you can take derivatives. Okay? And it's an exercise to compute the gradient of this term. And if you do it, this is what you get. Okay? By the way, these slides are fresh. So if you see typos and stuff, please take notes and let me know at the end. Yes? D. Yes, so when we take linear models, we also assume that X is RD. In fact, it can be a subspace of it doesn't matter, but we're assuming the input space to be RD. Okay, so for now and for a little bit, we're going to assume that it is RD. Then we're going to move at the same time to non-linear functions and non-Euclidean spaces at the same time. Okay, so as I was saying, if you see typos, take notes so that when we put them online, they're a bit less disgusting than now, maybe. So if you compute the gradient of this is the quantity you get. Okay? You stare at it a little bit, you see it's not too ugly, but the way it depends on W is complicated. So if you just, the thing that you typically want to do when you have a functional is that you compute the derivative, and then what do? Set the derivative to 0 and see if you get something reasonable. Okay? But here, do you get something reasonable? Well, there is a complicated, you get a nonlinear equation, okay? There is a complicated, W here is nice, but here is complicated. So if you set this quantity equal to 0, then you have to solve the complicated nonlinear equation to get back W, okay? So one way to tackle this, the standard way to tackle this is what? How do you get an approximate solution of that problem, given that you can compute the gradient so nicely? Gradient descent, okay? What is gradient descent? The idea of gradient descent is you take a function, you start from a point, you compute the gradient, and then from that point you move in the direction of the gradient, of a length that you decide. And then you keep on going. From a new point, you recompute the gradient, and you take another step. If you choose the step size good enough, you can show that you converge to the right point, which is the minimizer. Okay? Don't look at the equation too much, just think 1 second. If you have a function and you want to be sure to choose a step which is long but not too long, what will depend on? Which feature of the function it will depend on? So you take the gradient and you want to know how big is the step that you have to do. If you have a function, if you think a second, it will depend on how curvy is my function. If my function is very flat, I need to take relatively big steps, okay? If my function is very curvy, I want to take smaller step at some point because I want to get closer to the right point, okay? Just intuitively. And what I show you here is, most for your future reference, is basically the basic theorem that tells you that this is the case, okay? It basically says, if you look at the function, which is convex and smooth, and let's say strongly convex so that the minimizer is unique, then essentially if you look at how curvy is your function, you just take a good step size that ensures that this iteration goes in the right place. And what is this iteration is exactly what I promise you. You start from a point, let's say 0, and then you update taking a step in the direction of the gradient. Okay, so this 1 over L is the step size. I give you a condition above on how to choose it. The important bit is that in gradient descent, there is a standard way to choose this a priori. It's a constant. It doesn't have to be decreasing. It's constant step size, which is kind of holy grail of descent methods and iterative methods, because you don't have to fumble on the decay of the step size. You can just choose a constant, and that's it, and you can take big steps. So this is indeed possible if your function is smooth. And in that case, you have to compute this quantity, you have to compute the gradient, and then you can just run this algorithm. And here is just a pictorial representation of that. Okay? So this is the very standard way to solve a problem which is convex, perhaps even strongly convex, and smooth, but for which the solution doesn't have a closed form solution. All you have to do now is just to jump in and plug. Basically you have to replace f here with the function we want to minimize. But we already compute the gradient, and here is all you have to do. Okay? What is the cost of this iteration? How much does it cost me? So suppose that the way we compute complexity of a problem is just by saying that the cost of multiplying two numbers is 1, and then we just count how many real number multiplication we have. This is the numerical analyst way of computing complexity. How much does this cost me? This costs me nothing. It's just a number times a vector. How about this? How much does it cost me? If the dimension of the input is d, that costs me exactly d. Okay? And how many times I have to do this? N. So the cost of this is nd times the number of iterations you have to do. Okay? Not too bad. And it's simple enough. It's an algorithm that only requires vector-vector multiplication. And of course, there are tons of ways to try to approximate this and make it fancy. Okay? When should you stop? Well, you have to decide a stopping rule. For example, when the value of the objective function doesn't change much, or when the value of w doesn't change much. So there is a hidden threshold, which is when you have to stop, okay? And this is a numerical aspect that you have to decide, and it might not be easy, okay? Yet the algorithm is very simple. It's good enough for everybody? So the logistic regression serves us as the first example to try and make it a bit more complicated and consider the case of SVM. SVM, if you remember, is the case where instead of the logistic loss function, what we consider is the hinge loss function, which is this loss function which is linear and then becomes flat. It's nice because it is a tight relaxation, because it has the same target, the 0,1 loss, but the only problem is that there is that one point where it is not differentiable, okay? So here, this is strongly convex, but it's non-smooth, okay? Not horribly non-smooth, but there is one point where it is non-smooth. Now, this is by no means an introduction to the topic, but just to give you an idea, because I think it's simple enough, there is a notion of derivative that generalizes the notion of, the standard notion of derivatives to the case of functions that are convex but non-smooth. Okay? So of course it's not the usual derivative, but it's simple at least in one case, the unidimensional case. So let's just think about that for a second. Just look at this plot. Okay? This is a function which is differentiable everywhere but here. Okay, so in all these points, if you look at the left and right derivative, they coincide. But if you look at here, they don't, right? Here is whatever it is, this slope, and here is whatever is that one. One is going to be like this, one is going to be like that, and they do not coincide. There is a whole set of derivatives in the middle. Or if you want, there is a whole set of lines tangent to this point in the middle of these two extreme slopes. Does it make sense? This set of slopes, it's what is called the subdifferential or subderivative. Okay? If a function is convex, in each point you cannot just attach one thing, the gradient or the derivative, but you can attach a set of things. Okay? Not one, but many. Does this make sense? This is my hand-waved explanation of convex analysis. So the reason why I'm making it, because this seems to be a reasonable enough, these observations are reasonably intuitive, right? So you can imagine pretty much everything you know is going to get more complicated, but you can kind of see that some stuff might remain similar, if not the same. For example, to check if a point is a minimum or a maximum, what do you do? If the function is smooth, you take derivative, we just said it, and you set it equal to. Here, you cannot do it, but what can you do? You have a function that, say, looks like this one, okay? Or, say, the absolute value. What do? You can check in this interval of all possible direction to see if 0 is inside, okay? So let me just jump ahead 1 second. So it's a bit complicated, okay? But don't look at this equation, don't stare at that. But just intuitively, okay? You basically say, look, if my function goes from, if the derivative in that interval, up, if they go from like this to like that, at some point they're flat, and in that point it must go, you might have a minimum, okay? This is the idea. It goes from like this to like this, and somewhere in the middle it has to have a minimum. If it's continuous, it's really intuitive, right? Of course, it's a bit more complicated. Not only that, the idea could be, well, if I have just one derivative, I can take a step in the direction of the gradient. What if I don't have just one, but I have many? Well, the idea is that, you know, I can take one of those. Okay, they might not be exactly in the right direction, but eventually they should be roughly in the right direction. Okay? Does it make sense? So, if you have subdifferential, this is a complicated story. You don't have just one value, you have an interval. But if 0 is in the interval, then it means that it's a minimizer. That point is a minimizer. And if you want to grade gradient descent, well, you cannot compute the gradient. But if you can select an element in this set of possible derivatives, one such derivative, then you can try to use it. Does this make sense? So all the complication you see here doesn't matter. These two things I just told you and this plot are meant to convey the main informations, okay? The rest is details so that you have a reference for yourself in the future. Almost, I almost thought it was a question. Okay? So the main thing we want to do now is to say, this is basically the whole idea of subgradient methods. Okay, what they want to say now is, instead of gradient, we want to do the subgradient. And what's written here is basically, you know, what you should see in there is basically, I can do something like what I did the gradient, but instead of taking the gradient step, I have to get a subgradient step, which means that among these directions, I have to pick one, and then I have to take a step in that direction. Okay, of course, the complication thing is, okay, how do you pick this direction? What you see that we basically are going to be lazy, and we're going to choose the left derivative, for example. We can choose any of them, and we're going to take the left derivative, because it's easy to compute. This is going to be our selection criterion, and luckily enough, everything goes smoothly here. Okay, so same as gradient descent, you have to select one of these directions. We're going to take the left derivative. The theory of this algorithm is slightly different. And again, here what you should basically see is that the main difference is that, remember before I could choose a constant step size and just take steps depending on the curvature. I cannot anymore. I have to take a decreasing step size. So what you see here is that there is a so VT is going to be one of these direction. Then depends on the point WT where I'm sitting. Gamma t is the step size, which in this case has to be a decreasing sequence. There will also be some constant, but it doesn't matter because at some point the decaying will be the most important part. Okay, so take-home message, function is convex, non-differentiable. I can still take a subgradient method, which basically what I have to do is to select one of the derivative and then take in decaying step size. Okay? The final algorithm is going to be very simple. And this is how it looks for SVM. It's SVM if you want on the original parameter. So this one is always the same. It's 2 lambda WT, just the gradient. And this thing here is a bit more complicated. And again, you can just check that what we did is just computing the left derivative. You basically have to check. In one case, this will be equal to 0. Okay? When it's not equal to 0, you have to go and check the derivative. But the left derivative is just -1. Okay? And this is exactly what you get. So again, if you look at this algorithm, what you see is that it looks almost the same as the gradient descent. The step size is no longer constant, it has to be decreasing. Here I have to make this computation of the left derivative, and this is the cost of computing those things. Okay? I'm skipping here how the computation of the left derivative of this, but this is what you get. You can double check. It's easy and it's not the purpose of this discussion. How much? So we're quite happy, okay? This is a simple algorithm. The intuition is exactly the same as gradient descent, so you can think about it the same way. If you want the distinction are not the subject of this class, okay, although it's interesting in its own right. You can ask yourself, how much does it cost to compute this? How much does it cost? Again, for each point, you have to compute this constraint. This is going to be the main thing, right? And this costs me, again, D. Okay, because it's just the product of WT and XI. And how many times you have to do it? N. Okay? And you do see that you might produce, you have to do this for as many iterations you do. You do see that you might produce sparse coefficients here, but in fact, in subsequent iteration, they might get back to have a value different from 0. So there might be sparsity in the solution, but you're not ensured that this is preserved throughout the iterations. Okay, let me say, this is to some extent SVM in a 2016 version, okay? The classical way to derive the algorithm for SVM is to take this functional, put some optimality condition, do some fairly complex convex duality theory, and derive a dual problem, which turns out to be what is called the quadratic programming problem. Pretty much all the things I said require advanced stuff, and stuff that is not particularly enlightening, okay? But beware that you can, be aware of the fact that you actually look online. You find a lot of solvers based on quadratic programming techniques or interim point methods techniques, okay? My point of view at this point is you don't need to know that, you just need to use them. And if you really want to look at the details of how it's solved, you can do that. But you have to spend a bit of time not studying machine learning, but just studying optimization. This one version here is typically the one that you can handle when you work on very high dimensional data because it's simple. Typically, there is a whole trend in the last few years to use first order methods because they allow to just reduce the problem to matrix vector multiplication, which is what you can do when you are in high dimension and big data sets. Okay, so this algorithm, although ridiculously simple, turn out to be pretty effective when you have to go in high dimension. And of course, this is just a simple thing, right? You can do gradient descent, you can make gradient descent faster. There is subgradient descent, you can try to use other techniques to make it faster too. So this is just a glimpse. There is a whole literature on how to speed up iterative methods. The reason why I choose to present you this is because once you see logistic regression, with a little bit of stretch of the notion of derivative and gradient descent, you can introduce a way to solve SVM. Okay? Now, does it make sense? So we're in a relatively good shape in the sense that we have two examples of regularized algorithm that we can solve through iterative techniques for linear models. Okay? Of course, the question is, can we go beyond linear models? But before doing that, let's ask another question. Look at this complexity. Can I do anything better than this when n is much, much, much smaller than d? Okay? Suppose that d is smaller than n. It turns out that is actually pretty good complexity. But what if n is much, much smaller than d? Okay, this might be because I have few points, or because in a second, rather than the variables, I'm going to use features, non-linear features. So I'm going to make them big. Okay, so this is a relevant question in any case. So the whole idea of the representer theorem, which is typically associated to the idea of using kernels, can actually be reset in elementary terms as a potential answer to this question that I just asked. Okay? So this is, again, a kind of a fresh view on this. And the idea here is, usually, if you're in linear model, this is what you want to compute, okay? But if you can prove, okay, you have to prove it. If you can prove that, in fact, you can rewrite this function this way, or if you want in other terms, that the W you're looking for is not any W, but it's a W which is a linear combination of the xi's. Okay, so here it's written that if I can prove that the W I'm looking for is always a linear combination of the xi's, so here Ci is just a number, and Xi is a vector of the same size of W. So if I can prove that the W I'm looking for can be parameterized like this, then I could replace the optimization over W with the optimization over this C1 Cn, which is now the size of the training set, is exactly the size of n. So if I could do that, potentially I could go from optimizing something in D to optimizing something on n. And then I can decide which one I want to use. Okay? So what we want to do next is show that both for logistic regression, for SVM, you can do exactly that. Okay? Again, here I'm saying if you could do this, then you could really break down the complexity from D to N. Let's show that we can do this for logistic regression and SVM. So to prove it, okay, I'm skipping the proof, but the proof works like this. Well, no, let me show you the statement before the proof. you can prove that the gradient descent iteration for logistic regression that I just showed you, in fact, can be always written like this. So at step T of that iteration, I'm going to have that the W I'm looking for is exactly the form I wanted. So it's exactly a combination of the training set points with weights, and the weights are going to be given by this iteration. Okay? So this is exactly what we were hoping for. We were hoping, so this is not the proof, this is the statement, okay? We were hoping that we could rewrite a logistic regression in an equivalent way that depended only on coefficients C1, Cn. Here is the iteration you have to use. Okay, his CT here is a full vector, okay? And here I'm updating all its components. And what you see is that the expression is very similar. If you look closely enough, you see that here instead of xi, I now have to put an element of the orthocanonical basis, okay? So the point you have to see from this equation is that it's actually really, you can really prove that logistic regression can be written in an equivalent way just on the CIs. And the expression is as easy as the one before. Okay? Now.
Yes. Here is 1 plus E, there is no minus.
Where? Here. Exactly. Yeah, you're right. It's going to be like this in all the slides because I corrected it before because I got confused. So it's plus everywhere here. Okay, the numerator of the gradient is going to be always with a plus. Okay, in the exponent. Yeah. Yeah, we're going to fix it in the slides this afternoon. Okay, so how do you prove this? Okay, we don't want to prove it, okay? But how do you prove this? The way you prove it is by induction. It's one line. So basically, you start from this expression. No, where is it? You start from this expression, and you assume that what you want to prove is true. That is that the W, at each iteration, the W is really a combination of just the training set points. And then by induction, you can prove it, and it's one line, okay? I'm skipping it because that's not the purpose of this class, and because it's really a simple exercise. So I invite everybody to just do it once. You take this expression, you assume that each WT is actually some coefficient CT multiplied by the matrix of the x's, okay? And then by induction, you prove that this iteration holds. Okay, so the proof is just like that. It's very different from the usual representer theorem. In the usual representer theorem, what you do is that first of all, you show that the minimizer of the regularized functional has certain shape, and then you keep on going. Here, instead, we prove that the iteration of gradient descent can be represented through coefficient CT, which is more, directly what we want to do. And then we just show the explicit expression of the algorithm in this case. Okay? So the good news here is that if you look inside this algorithm, this in some sense only require this multiplication here. Okay? So before discussing complexity, let's look at the SVM. Here again, the story is just the same as before. If you start from the subgradient that I just showed you, by induction, you can prove that in fact, at every step, the solution can be written this way, with the coefficient satisfying this recursion. Okay, it's exactly the same reasoning as before. Take logistic regression, now you have the same thing. The main difference here is that you have to replace W with CT, and here instead of you have in some sense the new version of the subgradient of this quantity. Okay? So again, I'm skipping the proof here, but it's very easy. It's just one line by induction, and what we achieved is that we have now two iterations. We have the iteration on the W's, or the iteration on the CI or CT. Okay? And now we're in a good shape, because depending on which one is big, we can use one iteration or the other. The good code of this would basically be a code that says, if you want to use linear functions, go in, check which one between n and d is bigger, and then use the corresponding solver, either this one or the one on the w's. Okay? If you go in and check the computation, what you see is that you go from this computation to this computation. So effectively, when n is much smaller than d, you can indeed have a pretty big boost. Okay? Most importantly, you will see that in many situations, we will be able to use this idea to go beyond linear models. Okay, so I'm making a bit of a jump here, okay? So again, what we're doing here, let me summarize a bit before we move on. Our goal was start to take some regularized algorithm with penalization in the simple case of linear functions, and then see how to compute the solution. And the take-home message here is use first-order methods because they're simple. They can be used for the smooth case, gradient descent, but also for the convex non-smooth case through subgradient techniques. And while the derivation is a little bit different, what you should appreciate is that the expression you end up with is simple in both cases and reduces only to matrix vector multiplication. Okay? Then we took a step further and we said, can we reparameterize the problem in the case where n is much smaller than d? Can we rewrite the iteration in such a way that rather than w, we have a new coefficient c to optimize? Okay? And c should be the size of the training set rather than the dimension of the input space. And I skipped the proof, but we can do it as you can do it as an exercise. The answer is yes for both logistic and SVM. Okay? So we now have simple ways to solve both problems in the linear case, either when n is bigger or smaller than d. So what's missing? Well, first of all, one thing that through this derivation, as I told you, I'm really destroying the whole narrative of SVM of the 90s. It's just gone. There is a whole story that talks about margins, duals. It's all gone, okay? One thing that perhaps, I feel kind of guilty of killing completely is the name of the algorithm, because that has a long history. Super vectors, okay? So again, the nice thing of, you can actually derive some condition that give name to the algorithm. Doing it is not complicated. It could be done in basically half an hour, but we don't have half an hour here, okay? So I'm just gonna point you to the steps to do it, okay? Which are relatively easy, okay? So let me just tell you, before I show you some equations, the basic idea. Remember that a second ago we said that in the case of convex functions that are non-smooth, you cannot just set the derivative equal to 0. You have an interval and you have to have check that the 0 is inside. Remember that? Okay. Take-home message is you don't have an equation, but you have to check that something is in an interval. Okay? That's what you need to do. Clear enough? Now, if you write complicated equation and you try to be precise about what I just said, you have to basically, this something has to be in some subgradient, and then you have to go in and make the computation explicitly. You can do it, okay? And then you do some more computation that are also relatively simple, because you just have to compute left and right derivatives, but totally beyond our purpose today. And you end up discovering that indeed you have some condition on the coefficients of the best possible solution within some interval, okay? And this is what I wrote here. And this is the stuff that we want to take a look at. Everything else is the story that you have to verify that the optimal solution satisfies some inclusion, and you have to compute left and right derivative of something, okay? Again, it's elementary, but it takes a bit more time than what we have. What is written here is that the best solution to the problem as coefficients that has to be in some interval, as we expected from the beginning. But the interval has some meaning, okay? It basically says that if the function, the optimal function, has coefficients, if the optimal function at the point correctly classify the point, not only correctly, but also by a bit. So here you see it says, if this would be, sorry, this is a typo, it should be yi fxi. So if I take an xi, I compute fx, I multiply yi, and not only the product is positive, but it's positive by 1, okay? Then the coefficient associated to that solution will be 0. So not all the points have the same coefficients. Remember that the CI are as many as the training set points, and if you basically check the optimality condition, you find out that certain points will not matter in writing the optimal solution. And you can know what are these optimal points. They are the points that are correctly classified by a margin of 1. Okay? This is the famous margin popping out. If the points are either sitting on the margin or below the margin, so they can be correct but not by enough, or can be wrongly classified, then they do appear in the solution. Okay? And this is the classical pictorial representation of that. You have the points here are correct, and this is the distance 1 to the level set 0. Okay? So the points that are correctly classified by a bit will not appear in the explicit expression of the solution. The coefficients will be 0. The other ones will appear. All the points with the coefficient different from 0 are what we call the support of the solution, are the support vectors, okay? Are the building blocks that you need to write down the solution, whereas all the others will not appear, okay? So this is what gives the support vector machines is this algorithm where the solution can be written depending on only a few points, okay? If the number of supervectors is very small, you can show that there are algorithms that can exploit this to further reduce the complexity of the method, okay? Which you expect, because we said that the point scale is n, but really, if most of these points don't appear in the solution, I should be able to exploit this. Suppose the number of supervectors is 1/10 of the total number of points. You should be able to exploit this, at least in the average case, to get even better complexity, okay? So again, the take-home message here is there is some simple but slightly longer than we have the time to explain math that shows you that just simply by checking the optimality condition of an SVM, you get that the solution has to satisfy these constraints that are called box constraints that do give rise to the nomenclature supervectors that are the points for which the coefficients are different from 0. Okay? So I'm expecting both the subgradient perspective and this perspective, the optimality condition perspective to derive supervectors to be new to you. Okay? But the good news is that they're much simpler than what you were studying before. Okay? Both the QP derivation and the Kuhn-Tucker dual, it's much more complicated than this. To do this, you have to know two fancy concepts in math, which are the left and the right derivatives. Okay? Not true. I mean, you also have to understand a bit what is the subgradient. But, you know, once you believe it, all you have to do is left and right derivative. Okay? So it's really short. Okay, so let's kill one question and move on. Okay? Are loss functions all the same? No. Okay? For at least two orders of reasons. By choosing the loss function, you're changing the target of your learning problem. By choosing the loss function, you're considering different kind of computations, okay? In this case, they're pretty much equivalent from the computational perspective, but you do see that logistic and SVM don't have the same target. One is estimating the conditional probabilities, whereas the other one is just choosing, you know, yes or no, okay? Just choosing the Bayes decision rule. What is the best choice for my problem? Well, it's your problem, so you should choose it, okay? There is no global answer. Depending on the problem you have, do you care about the densities, the confidence of each estimate? Maybe logistic is better, okay? You don't care and, you know, just something robust is fine enough? Well, you go for SVM, okay? Subgradient is slow as hell, but you have a fast way to improve speed of convergence of gradient descent? Well, go back to logistic regression, okay? These are the kind of consideration that guides in the choice of the loss, okay? Either modeling consideration or computational considerations, okay? So, now, if you're still not awake but alive, the good news is that to some extent we sweat what we had to sweat because a lot of things are going to be for free now, okay? For example, we're sticking to the linear model, but what if I choose a non-linear model given by a bunch of features? What do you think is going to happen? Almost nothing. Okay, basically, instead of x, you have to now consider this phi of x. Okay, whenever you add an x, you now have a new variable, you call it phi of x. And the rest is all the same everywhere, okay? So think you have a preprocessing where you take all your inputs, okay? And you spit out for each input vector its new representation, phi of x, that you compute this way. So you have a machine that computes this for all the input points. From a computational perspective, up to this preprocessing is all the same. You have that you can do the gradient descent, you can do the subgradient descent, you have to do with the W, you can do with the CT. It's just the same, okay? As you see, what might happen is that if you choose P large, which you might want to do because you want a big dictionary, then it might be that the version where you use C instead of W is the one that you want to use. Because you see that before it was just a matter of how many variables you have, here is how many features you choose to use. Okay? So it might be interesting to allow yourself to use a complexity driven by N rather than P. And here I just repeat what I just said. Okay? Again, to be fair, in the linear case, all you have to do is this. Okay, so in the case you parameterize your function with W, all you need to do is this replacement. Okay, a preprocessing doing that. In the case where you want to parameterize with C, before we have this expression, this is the face of the representer theorem in the linear case. If you're using nonlinear features, this is the face of the representer theorem. Okay? And again, I did nothing but replacing x with phi x. So the W case is really just the same as before. Here we write the C case. If you look at this, this line is exactly the same as in the linear case. It's exactly the same, okay? You can stare at it as much as you want, but there is no difference. The difference is that this FT is now written this way, okay? So you need to have your new feature map. You just use it, and that's it. So again, we start from the linear. I hope you appreciate that we start from the linear case, because once you move from the linear case to the case of finitely many nonlinear features, it changes the hell of a lot in terms of modeling, right? Because we're doing from a line here to something complicated. So modeling, it changes everything. But computationally, it's almost the same, okay? The only difference is that everything is going to scale with the number of features rather than the input dimensions. Okay? All right, so logistic, SVM, linear functions, parameterization in W, parameterization in C. Moving to linear features for free, okay? Completely for free. There's nothing we can think of, okay? What's left to be done here is just moving from parametric to non-parametrics. What do we mean by parametric and non-parametric? What are you thinking of when you think of non-parametric models? You're thinking of pasta asciutta right now. Again, what I told you before is a parametric model is a model where I choose a priori the number of parameters in my model. A non-parametric model, this is not the precise definition, it's a running definition, is a model where the number of parameters in the model is chosen by the data somewhat adaptively. Okay? Now, if you look a second about this expression, what you see is that my choice of parameter is hidden in phi by the number of coefficients in this expression is how many? It is a hard question, huh? It's n, okay? So you have as many coefficients as the number of points, which means that if tomorrow I give you twice as many coefficients, then you have twice as many, sorry, if I give you twice as many points, you have twice as many coefficients. Of course, as we told you before, this is, right now you cannot play this game because the game is which one is bit between n and p. At some point, it will be better to switch back. So suppose n is small and p is large, because I chose it that way. I say, oh, my p has to be super large because my problem is hard. Then I say, oh, I stick to this, and I get n points, 2 n points, 3 n points, and so on. At some point, that number of points is going to be bigger than p. I have to switch to the computation, and I'm back to basically not using enough dimensions. Okay? The problem can be poor. So the idea here is a kind of a trick, which is so deep that it's going to be impossible for me to explain in any of its depth. And I'm just going to present it as a trick. Okay? The trick here is maybe there are situations in which I don't know how to make a big vector of phi, but I know how to compare two x's in a smart way. So look at this equation, which is the one that we've been using so far. You can view it as I take x, I take x prime, I take their features, and then in some sense, through the inner product, I compare the features. And so I compare x and x prime. Correct? What if I have a way to do this implicitly to a function k? So instead of defining a phi that does this job, I take some function k that compares the two. That makes sense? It doesn't quite make sense because it's super abstract, okay? The thing is to find good example of k. But what you see is, so let's say it in another way. Take all the equation that I just showed you, and whenever I had this expression, replace it with this expression, okay? Let's see what happens, okay? This is a fair question, okay? Let's see what happens if we do that. We take all the expression we had where this quantity was appearing, and now we just use this new symbol, k of x prime. Let's see what's going on. Well, first of all, the function, this expression here, just looks like this now, right? I'm gonna kill poor reproducing canonical spaces as a mere change of notation here. So this is just take this expression and use this change of notation. Let's see the computations we saw, for example, for logistic regression and SVM. As I pointed out already, this expression almost didn't change. All that changed was the ft that is hidden in here and it appears in here. And now ft is just going to be like this, okay? So again, before I told you, do a preprocessing that take x and spits out phi of x. Now I'm telling you, do another preprocessing that given all the x, compute k, xi, xj, and then use the entries of this matrix that you want, okay? It's the same. So if I replace phi transpose x with phi x with k of x prime, computationally, I only have to replace one preprocessing with another preprocessing. Okay? Just the same. Correct? What am I achieving with this? Well, if this is really just a change of notation, so you can always write phi transpose phi or k, this will be the same, okay? But it turns out that there are there are kernels for which you can compute this easily, and you know that some phi exists, but you cannot compute it, okay? It exists, but you cannot really compute it. So let's make some example. Let's make two examples where indeed I give you a kernel, okay? And you can check what is the corresponding phi. The first example is the linear kernel. The linear kernel is just the inner product of x and x prime. What is phi in this case? This is pretty hard. It's nothing, it's the identity, okay? You do nothing to this, okay? This is a trivial case, okay? It's the clear case where they coincide. Let's look at the second case, and if you want, forget about that one even, okay? You have a kernel, in this case is x times x prime plus 1 to the p. So it's some kind of polynomial thing, okay? Can you write that as phi transpose x, phi x prime? Is the question clear? I would like to write this in this form. Can you do that? How do you define a phi x that give me that? Well, you could write, suppose that this is, for example, degree 2. Let's make it simple. How would you do that? How can you write down a degree 2 polynomial? You can take the vector x, which is going to be a bunch of coordinates. So you take x is going to be x1, x2, xd. X prime is going to be the same. And then what do? You take x1, x2, xd. Then you take x1 square, x2 square, x3 square, and you keep on going. Then you take x1 times x prime 1, x2, okay? You take all the monomials that you can build out of two vectors, and then you multiply them, okay? You order them and you multiply them. And you can write any polynomial as a product of a bunch of monomials, right? So the explicit feature map that you can associate to this kernel is just the one that sends each vector and its coordinates to all the possible monomials that you can build out of these coordinates, all right? What if I take a polynomial degree bigger than 2? Well, you have to take more and more monomials, okay? how big is the dimension of the feature space? How big is the phi I'm building? I have dimension d. I have a polynomial of degree p. I have to build all the monomials. First of all, are they going to be infinitely or finitely many? They're going to be finitely many, and a lot. They're going to be essentially exponentially large in the dimension of the space, but they're going to be still finitely many. So what you see is that in both this case and this case, each kernel is associated to a feature map that you can, in principle, compute explicitly. It might be painfully, as in the case of the monomials, but you can compute it explicitly, and it might be, as in the case of polynomials, very high dimension. Okay? The last example is the case where each point, the kernel is given just by this expression, which is what is called the Gaussian kernel. Okay? Think of it as a way to, again, to compare 2 points. What does it say? If you take 2 points, you compute their distance, but then you zoom in, okay? So if this distance is small, the 2 points are going to be similar. But if the distance is big, by putting this gamma here and putting everything on top of an exponential, I'm killing the similarity of the 2 points, okay? So from that perspective, it kind of makes sense. You take a k, okay? Which is just an exponential with some gamma. So if you now take 2 points, if they're close, they're similar. But if they're a bit far away with respect to gamma, my exponential is just going to kill them. So from the perspective of comparing 2 points, it does make sense. Okay? Can I write a feature map? Okay? Well, the answer here is basically yes and no. You can write it mathematically, and there are many ways of doing it. Okay? But there is no way to actually compute this feature map because it's infinite dimensional. So the dimension of the feature space, you see here. Where is it? I have it here. If you use the Gaussian kernel, you can write a phi, but really the space you're considering is an infinite dimensional space. How do you convince yourself about that? Well, the space of polynomial of degree p is a finite dimensional space because it's a combination of just monomials. A combination of Gaussians doesn't have any regularity like this. You know, if you combine infinite Gaussian and arbitrary number, you can do whatever you want. Okay? So again, there is no particularly friendly way of showing why it's infinite dimensional, or if you have it. But at least we can get a feeling of what we are doing when we combine those things. Okay? So what we can do is basically say, okay, now we're going to go back to our expression, and we can see that instead of thinking in terms of feature maps or combination of features, we can think in terms of combination of kernels. For example, if you combine kernels at points xi, what you're going to get? If you use the linear kernel and you combine the points in this way, what you're going to get? Well, it's easy to see that you just have linear functions. Okay? If you use the polynomial kernel and you plug it in here, you're basically going to take in each point a polynomial of degree p, and then you combine them. And then what do you get? Some polynomial of degree p. Okay? It's slightly less boring to do the case of the Gaussians, because at least you can shake your hands. So each of these k is a Gaussian centered at xi. Okay? You fix the width. So look at this, for example. This is just a Gaussian centered at this point x with a fixed width. Then I'm going to take another Gaussian fixed at another point here. And then another one, then another one. Here I have 6 points. Then I'm going to choose Ci, which is the height of this little mountain at each point. And then I'm going to connect the tips of the mountains. Okay? So you have a mountain here, mountain here, mountain here. You have to draw them up and then connect their tips. So what you see here is that intuitively the choice of kernels here also control how complicated is my function. If I take Gaussian, which are very, very, very large, basically everything is going to be very smooth, okay? Think of those Gaussians, red Gaussian, to be very, 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 very large. And basically, when I connect, the tips almost touch each other, so to say. So when I connect them, I just get something very simple. The opposite, suppose that those red Gaussians are very, very, very pointy, okay? Then I can have something in between 2 tips, a lot of stuff can happen. So I get a function which is very complicated. So we see that the choice of the kernels, as should be expected, control how complicated are my functions. Now, here, what you see are just 3 examples of kernels that are the ones that are off the shelves, okay? They're just the simple ones that you can build for vectors. But in fact, as in the case of features, we did something interesting here, which is, see, even here, a lot of stuff is going on in each of these phi, okay? In the linear case, we are assuming the input to be a vector. But here, I'm just assuming to be able to extract a bunch of numbers out of any input. So suppose, for example, that your input is a graph, okay? Then out of this graph, I can read out a bunch of numbers, the connectivity, the degree, the amount of connected components, blah, blah, and these are just becoming F1, my phi, okay? And then I can handle it as if it was just living in a vector space. Of course, the smart thing is how to extract these numbers. Who tells you which numbers are important, okay? I'm not telling you how to do that, but I'm just saying, if you know how to do it, you're game, okay? It's true for strings, true for all the rest. Does it make sense? So the moment you have complicated input, but you can select nonlinear features out of them, from a modeling perspective, you're good to go. In the case of kernels, it's the same. For all this, you might be able to, in some sense, build similarity measures, okay? Basically, I give you two graphs, and there is some smart way to compare them that doesn't go through writing them as vectors and then taking Euclidean distance, okay? Something different from that. And same thing for graph, for histogram, for sets. For example, I can have ways of comparing probability distribution by some Kullback-Leibler distance, for example, or some Kolmogorov-Smirnov distance, and so on. I'm not saying that this is easy, okay? I'm just saying that exactly how you can build in prior knowledge through choosing features, you can do the same by choosing kernels, okay? By looking at them as similarity measures. And there was and there still is a whole industries of proposals to build kernels for different kind of data. An actual question is any function of two variables a kernel, okay? If I come up with an idea about a similarity measure, is it going to be a admissible kernel, yes or no? And the answer is no. It has to have a couple of properties. The basic idea is, again, that we want to look at the kernel as a similarity measure or an inner product. And from a technical point of view, there are two conditions that your kernel have to meet. The first one is kind of innocuous to some extent, and it's symmetry, okay? You want your kernel to be symmetry. The order of x and x prime should not matter that much, okay? And in fact, it doesn't matter at all. The other assumption is somewhat technical, and is basically related to the fact that we want to look at this as an inner product, okay? It's easier to state, and it's just a technical fact, which in fact is not easy to check. He basically says, if I come up with a kernel K, and I can prove that now, you come up with a kernel, okay? You have some points, x1, xn, build the matrix, which is n by n, with entries xy, xi, xj, okay? You get this matrix, you could diagonalize, it's symmetric, you could diagonalize it, and if it turns out that all the eigenvalues are 0 or bigger than 0, this is a good kernel, okay? The problem is this has to be true not for just those points, but for any points, x1, xn, that you could select. So if you have a function that for any point x1, xn you could select gives you something like this, then you call this function, and this, sorry, a matrix like this with eigenvalues which are positive or equal to 0, then you call this function a positive definite function. Again, the name game is a positive definite function is one that induces positive semi-definite matrices, okay? So this is a technical condition, is the technical condition that defines what's an admissible kernel, okay? And you can check in one line that whenever the kernel comes from an explicit feature map, if I give an explicit feature map and I tell you check that it's a kernel, you can do it immediately, okay? So do it, actually. It's actually a nice exercise. Assume that the kernel is given by a feature map and show that it's always positive definite, okay? This is very easy to prove. It's a instructive exercise. For other kernels, for example, the Gaussian kernel, where I don't know how to give you explicitly a feature map, it's actually not easy. In the Gaussian kernel, say, for example, we use Fourier analysis, and it's, again, not complicated. But if you invent some crazy kernels of your choice, it might not be easy to prove that it's a kernel, okay? And that's why there has been a lot of work on this. This is more or less 3-4 classes I teach at MIT, and we killed it. Now, back to non-parametrics, which was our motivation, okay? I basically introduced kernels as just a trick that said, go in whatever we discussed, replace phi transpose phi with k, okay? That's all I said. Why did we do that to begin with? Because we wanted to go beyond parametrics. And again, that's basically what we did. Here, the dimension of the space of function you can build this way is depending on n, okay? You can easily check that the dimension of this space is n, and so the more points you get, automatically, the more is the dimension of the space you consider, okay? It's not you changing it, it's the model changing it, okay? And the algorithm is gonna potentially be computationally heavier because we have to compute more coefficients, okay? In this case, we don't have the W. In general, we don't have the W. Somebody fainted. Tell me somebody fainted. It would be epic. What? The door, probably. Okay. So here you don't have the W version because, again, the phi of x might not be easy to get. You know, you cannot compute it. But you always can compute it with the coefficient Ci. Okay? And so here we are happy because if you use kernels that are rich enough, for example, the Gaussian or exponential kernels, then we're really taking a model which we cannot write down as a simple parametric model. It's really non-parametric in the sense that it depends on the number of points. Again, non-parametric doesn't mean that you always have to compute infinite coefficients, okay? Infinitely many coefficients. This will be kind of sad because we don't have infinitely many computers. But it means that you just have a model that adapts its size to the size of the data sets, okay? All right, then I'm more or less done with what I wanted to say. Again, this class was the first encounter with the idea of regularization, okay? We didn't spend that much time introducing the different notion of regularizers because we somewhat stick to the most classical ones, which I assume you have seen before. What we did is that we somewhat reviewed logistic regression and SVM from the perspective of computations using first-order methods, gradient descent and subgradient. Along the way, we provided some new, no, not new, I wouldn't say that, but some more modern, simple way to solve SVM just by subsequent iteration of matrix vector multiplication. And I hinted you at a simple way to derive the support vector concepts through basically writing down the optimality condition, okay? And again, I encourage you to look a bit into that because it's simple and it just requires simple computations. Once we spent time on this first part, we moved from linear models to still linear models, but with an equivalence parametrization that now scales better if the number of points is much smaller than the number of dimensions. This is interesting in its own right, but it's so much more important if we have in at the back of our mind the fact that we might replace variables with features, okay? No linear features, because at that point, we are interested into making this number of features as high as possible. The good news is that when you move to this case of nonlinear features, everything is the same, okay? So you sweat a bit on the linear model because when you go to the nonlinear model, everything changes from the modeling perspective, but nothing changes from a computational perspective, up to small preprocessing. The last step we took, which is kind of a leap, is going from features to kernels, okay? And we presented this as a kind of a trick that allows to basically swap from thinking in terms of feature maps to thinking in terms of similarity measures. And we hinted at a few examples. Once again, the good news is that while we took a big step from a modeling perspective, we actually had to do very little from a computational perspective. So we now have a pretty large battery of algorithms because we have a couple of loss functions, but by choosing different kernels, we have a long list of different kind of functions we can implement with computation that are going to look essentially the same, because either you have to change the feature map or the kernels, but the code is going to be the same. So one good news is that the code of the thing I show you is basically the one line of the iterative methods plus the preprocessing for kernels or feature maps. So once you have to go down and use it, the main thing you will have to struggle a bit is how to choose the regularization parameter and how to be sure that your algorithm is working in the right regime. Okay? So this is what you were going to see in the lab. So what's waiting for you tomorrow? Essentially, debunking the idea that everything is penalization and everything is Tikhonov, okay? As I told you at the beginning, the idea that you just take an empirical risk and you penalize is so common that people end up even calling that regularization. Tomorrow what we want to show is that in fact there are other ways to regularize that are maybe similar from a modeling perspective, but they might be pretty different from a computational perspective with some advantage that in fact turns out to be important, especially in large-scale scenarios. Okay, so that's basically what we want to do tomorrow. And in fact, this is just the second class tomorrow is going to be about the case where rather than function with real values, you have function with vector values, okay, more than one possible output, which is a way to account for the case where instead of one problem, you want to solve many problems at once, because in some sense you believe that these problems are related. So by solving them at once, you can exploit relatedness. Okay? All right. That's all for today. If you have any questions, and otherwise I'm going to be here a few minutes more. Questions? Lunch?